In our final full chapter of the semester, chapter 21, we're going to use the principles of both equilibrium and thermodynamics to study once more redox reactions and talk specifically about electrochemistry. In review of what we learned about redox from General Chemistry 1, a redox reaction, or oxidation-reduction reaction, is a reaction that involves the net transfer of electrons rather than something like an interaction of ions. Electrons are transferred from something that loses electrons, a substance that we say undergoes oxidation, to a substance that gains electrons, a substance that we say undergoes reduction. Oxidation is the loss of electrons, rendering something more positive as a result, and reduction is the gain of electrons, rendering something more negative as a result. There are two mnemonics that we could use to keep these processes in mind. Either oil rig, oxidation is loss, reduction is gain, or Leo the Lion says grr. Loss of electrons means oxidation, gain of electrons means reduction. Along these lines, we also had terminology related to agents. In redox reactions, agents don't do the thing that their name sounds like they do. And just like an athlete's agent doesn't actively play the sport, they just arrange for an athlete to play it, an oxidizing agent doesn't get oxidized. It just allows for another substance to become oxidized. A reducing agent doesn't get reduced. It just allows for another substance to be reduced. And because in a redox reaction, electrons get transferred rather than disappear, an oxidizing agent, because it can't be oxidized, must be reduced. And conversely, a reducing agent, because it can't be reduced, must be oxidized. We can keep track of oxidation states or oxidation numbers for everything in a molecular compound if we remember some rules of electronegativity, and that the sum of all the oxidation states of all of the atoms that make up a neutral compound are equal to the charge on that compound. For a neutral compound, that charge is 0. For ions, the sums of all the oxidation states must add up to the charge of the ion. Almost always, the most electronegative element in a compound gets its preferred charge. And each atom of the same type in a compound will almost always get the same oxidation state. Elements by themselves, as free elements, even if they're diatomic, tetratomic, and so forth, have 0 oxidation state. The group 1A alkali metals have a +1 oxidation state. The group 2A alkaline earth metals have a +2 oxidation state. Hydrogen can be a +1 oxidation state with nonmetals, a -1 with metals, but it has no other options. So sometimes compounds with hydrogen form exceptions to the rules up above. So, as a review, let's assign oxidation states to each element in each of the molecules or compounds that are listed on this slide. Firstly, in diatomic chlorine, our rules of assigning oxidation states say that all of the atoms of the same type in a compound generally have the same oxidation number. And what's more is that all the oxidation numbers have to add up to the charge on a compound or ion. In chlorine, there is no charge. Chlorine is neutral. Therefore, the oxidation states of all the chlorine atoms must add up to 0, and they must all be the same. The only option that chlorine has in diatomic chlorine is to have a 0 oxidation state for every chlorine atom. In sulfur trioxide, though, in contrast, we have a neutral molecule with different elements, sulfur and oxygen. The most electronegative element tends to get its preferred oxidation state. Oxygen is the most electronegative element in this compound. It gets its preferred oxidation state, which is the same as the charge it would form as an anion, 2-. There are 3 oxygens, and since there are 3, there are a total of 6 negative charges. The sole sulfur atom has to compensate for all 6 negative charges or negative oxidation numbers by supplying an equal number of positive oxidation numbers. The oxidation state of sulfur, therefore, must be 6+ in this compound. We can apply a similar principle to the elements in HNO3. In HNO3, oxygen, the most electronegative element, gets its preferred oxidation state, which is 2-. Again, there are 3 oxygens, so in total, all of the oxygens together produce oxidation numbers totaling 6-. Hydrogen, because it's with nonmetals, produces a +1 oxidation number, one of its only 2 options. And therefore, as we stand right now, we have 1 positive oxidation number from hydrogen, 6 total negative charges from all of the oxygens. What does that leave left for nitrogen? But a 5+ oxidation state. So that we have a total number of positive oxidations that are 6+, a total number of negative oxidation states that are 6-. In an ion, all of the oxidation numbers have to add up to the charge of the ion. In dichromate, therefore, all of the oxidation states of all of the chromiums and oxygens will add up to -2. Again, oxygen is the most electronegative atom in this ion. It gets its preferred oxidation state, which is 2-. In total, all of the oxygens contribute 14- for oxidation numbers. That means that all of the chromiums together need to total how much? 12+. That's right. Because if all of the chromiums together total an oxidation number of 12+, while all of the oxygens together contribute an oxidation sum of 14-, 12+ plus 14- gives us the -2 charge on this dichromate ion. Each chromium will produce the same oxidation number, and since there are 2 of them, each chromium is 6+ in this ion. In OF2, the most electronegative atom is fluorine, and it gets its preferred oxidation number, which is 1-. In total, there are 2 negative oxidation numbers produced from all of the fluorines together. So therefore, the oxygen has to have an oxidation number of 2+. We use these oxidation numbers and oxidation states to track which things have been oxidized, which have been reduced, which are oxidizing agents, and which are reducing agents in a redox reaction. So, suppose that we wanted to investigate the reaction of iron 3 chloride production from elemental iron and chlorine. In this reaction, iron reacts with chlorine to produce FeCl3. In balancing this reaction, what we can say is that we need a coefficient of 2 on the right-hand side, a coefficient of 2 in front of iron, a coefficient of 3 in front of chlorine, and we're balanced. Not too tough a balancing act. We can also assign oxidation states to all of the elements on each side of this chemical reaction. For example, iron must have a 0 oxidation state because it's an element all by itself. Chlorine must likewise have a 0 oxidation state. It's in its elemental form, diatomic chlorine. However, on the product side, in the compound iron 3 chloride, Chlorine is the most electronegative element and gets an oxidation state of -1. Iron must have an oxidation state of +3 to compensate for all three of the chlorines' -1 oxidation states. What we see if we look at how iron has changed, going from reactant to product, it has gone up in oxidation state. Anytime something has gone up in oxidation state, it's become more positive. Up in the air is oxygen, and up in oxidation state means something has oxidized. So we say that iron has undergone oxidation in this redox reaction. Contrast this with chlorine, which has gone from a 0 oxidation state on the reactant side to a -1 oxidation state as a product. We say that because chlorine has gone down in oxidation state, it's reduced its oxidation state to something more negative, that it's undergone reduction. So going down in oxidation state, reducing your oxidation state, is indicative of reduction. In this reaction, the element that got oxidized is iron. And the element that got reduced is chlorine. In alternative terminology, we can call a reducing agent a substance that contained the element oxidized. On the reactant side, the substance that contained the element iron was iron all by itself. And we can call an oxidizing agent a substance that contained the element that got reduced. The element reduced is chlorine, and the substance that contained chlorine is Cl2. One final way to show all of this information is through a so-called half reaction. A half reaction is a bookkeeping measure that helps us track oxidation and reduction. A half reaction will show stoichiometric balance and charge balance, meaning that we'll have the same numbers and types of atoms on both sides of a half reaction, and we'll have the same total amount of charge on both sides of a half reaction. We'll write down one half reaction for oxidation and one half reaction for reduction. Adding them back together will give us the overall net reaction for a redox reaction we're interested in. For example, we can write down half reactions that show precisely the mechanism by which iron is oxidized and chlorine is reduced. For this particular example, the oxidation half reaction will show what happens as iron loses electrons, as it produces the electrons for this reaction. Iron goes from being Fe with a 0 oxidation state as a reactant to being Fe with a +3 oxidation state as a product. This already shows stoichiometric balance. We have one iron on the left-hand side of this half reaction, and we have one iron on the right-hand side, but it does not yet show charge balance. In order to show charge balance, we need to have the same total charge on both sides. Right now we have 0 total charge on the left-hand side, but 3+ charge on the right-hand side. In order to compensate for charge, what we're going to do is add electrons. Electrons are negatively charged, meaning that if we add electrons to the right-hand side of this reaction, we can reduce the total charge overall on that side. There are 3 positive charges. We need to make the net charge on this right-hand side 0, so we'll also add to this right-hand side 3 negative charges. This half reaction tells us that iron produces iron 3 and loses or generates 3 electrons. We can do something similar for a reduction half reaction. We can say that chlorine goes from Cl2 to Cl with a minus charge. In this half reaction, we don't yet have stoichiometric balance. We have 2 chlorines on the left-hand side, but only 1 on the right-hand side. So I can put a coefficient of 2 in front of the chlorine on the right-hand side. But notice what that does to this right-hand side. Not only does it affect the number of chlorine atoms, it also affects the number of total negative charges on this right-hand side. Right now, there are both 2 chlorines and 2 negative charges, 1 from each chlorine, on the right-hand side of this reaction. To compensate for those 2 negative charges on the right-hand side, where there are 0 total charges on the left-hand side, we're going to add 2 electrons to that left-hand side. What we'll say is that in a reduction half reaction, electrons are reactants, whereas in an oxidation half reaction, electrons are products. Oxidation is loss, or the production of electrons. Reduction is gain of electrons. These are our 2 half reactions. Next, what we're going to do is say that if we add these 2 half reactions back together, we're able to get our overall balanced reaction. This thing that we got so succinctly up at the top. So, in order to be able to add these reactions together, we need to show a net equivalence in electrons transferred. To add 2 half reactions together, we must have the same total number. We've got to have the same total number of electrons produced as consumed, so that electrons just go away in our overall reaction. Notice that electrons don't show up on the reactant or product side of the reaction up above. In order to do that, we're going to multiply both the oxidation and reduction half reactions by the simplest whole numbers that make the number of electrons produced in the oxidation half reaction equal to the number of electrons consumed in the reduction half reaction. The easiest way to do that here is to multiply the oxidation half reaction through by 2 and multiply the reduction half reaction through by 3. What we'd end up with for our oxidation half reaction is 2 irons yielding 2 iron 3 plus 6 electrons. And what we'd end up with for our reduction half reaction are 6 electrons plus 3 chlorine molecules producing 6 chlorides. And it's going to be these 2 reactions that we add together to get an overall reaction. I'll take this whole reaction here, now with an appropriate number of electrons, and add it to this reaction for reduction. When we add these 2 reactions together, the numbers of electrons being the same on opposite sides of a reaction arrow cancel out. And what we're left with at the end are 2 irons plus 3 chlorines produce 2 iron 3 cations and 6 chloride anions. Another way to say this right-hand side is to say that iron cations and chloride anions occur as an ionic compound, where that ionic compound's formula can be written as FeCl3. There must be 2 FeCl3s to give us the 2 irons and 6 chlorides required by this redox reaction. And sure enough, this balanced chemical reaction down here, achieved by adding 2 half reactions together, precisely matches the balanced reaction that we came up with up at the top. So it seems like we can use a whole lot extra work to show the exact same thing as we might have deduced from a general chemistry 1 treatment of this redox reaction. And that's true in this case. But this technique of writing out oxidation and reduction half reactions is going to be the sole determining factor in our capability of balancing more complicated redox reactions moving forward. For example, redox reactions that occur in acidic solution often have things available to them that we didn't take into account in previous reactions. For an acidic solution, we now know that there are major species like water and H+ cations available that might not explicitly show up in an overall starting skeleton reaction. This is an example of a skeleton reaction. It only shows the participants that are involved in redox, oxidizing agents and reducing agents. In this redox reaction, eventually what we'll find is that chlorate, ClO3-, is an oxidizing agent. It contains a substance that's reduced. And sulfur dioxide is a reducing agent. It contains a substance being oxidized. Ultimately, our job is going to be to figure out which one. And what's more is we're going to try to balance this overall reaction. Keeping in mind that if this reaction occurs in acidic solution, as stated here, that there are contributing alternative substances that might not be part of oxidizing agents or reducing agents, namely water, protons, H+ cations, and electrons that are being transferred. This skeleton reaction is impossible to balance all by itself. We're going to need to take into consideration the environment in which this reaction occurs and these contributing substances. To do that, the way we'll approach balancing this redox reaction is to split the redox reaction into 2 half reactions, one that represents oxidation and one that represents reduction. It really doesn't matter which one represents oxidation and which one represents reduction. We're going to figure that out in a little while. For now, in step 1, we can split our reaction up into 2 processes. One that somehow transforms chlorate, ClO3-, into just chloride. What we're going to do is group substances that contain similar atoms in a half reaction. Chlorate and chloride both contain chlorine. And similarly, sulfur dioxide and sulfate both contain sulfur. So we're going to put those 2 things together. Somehow chlorate becomes chloride, and somehow sulfur dioxide becomes sulfate. In order to deal with these 2 reactions, we're going to, one by one, balance both the numbers and types of atoms, and then balance charges. So let's start with the chlorate becoming chloride half reaction. We'll move this one down here out of the way for now. We need to balance the numbers and types of atoms, chlorines and oxygens. And I'm sure you're recognizing now that although we can easily balance chlorine, there's one of each on both sides of our reaction arrow, there is no oxygen on the right-hand side whatsoever, whereas there are 3 on the left-hand side. So you're likely saying you can't balance oxygens if there aren't any to begin with. But what we need to keep in mind is that this reaction occurs in acidic solution, where there are other key components, major species in solution, that we haven't taken into consideration for the purposes of this redox skeleton reaction, where we're just showing oxidizing agent and reducing agent. Those three substances are water, H+ cations, and electrons. In a reaction that occurs in acidic solution, if we ever need to balance oxygens, we can include some water in our half reaction to help us out. So let's do that here. Let's add in some water to help balance oxygens. We know we have 3 oxygens on the left-hand side. We're going to need 3 oxygens on the right-hand side. We can get those by including 3 water molecules in this half reaction. When we do so, we have balanced chlorine and we have balanced oxygen. But we have also introduced 6 additional hydrogens on this right-hand side, and hydrogen isn't present over on this left-hand side. If ever we need to balance hydrogen in an acidic solution, we can take advantage of the H+ cations that are floating around in an acid. I'm going to add 6 H+ cations to compensate for the 6 hydrogens that were produced by me adding water to the right-hand side. And now I should have an appropriate number of atoms of each type. 6 hydrogens, 6 hydrogens, 1 chlorine, 1 chlorine, 3 oxygens, 3 oxygens. My next step is going to be balancing charge. Notice that I have 6 hydrogens each with a +1 charge and a chlorate with a -1 charge. In total, right now, we have 5 positive charges on the left-hand side. On the right-hand side, we have 1 chlorine with a -1 charge, 3 waters with no charge whatsoever. So we have a 1- charge in total on the right-hand side. To balance charge, we need this last species, electrons. In this reaction, we're going to need to include electrons to balance charge. We'll always add electrons to the side with the more positive charge. In this case, the more positive charge is 5+. To get from 5+ to 1-, we need to take away 6 or add 6 negatives. I can do that by adding 6 electrons to the left-hand side. When we do that, what we end up with is now 6 negatives, 6 positives, and a negative. That gives us -1 charge on this left-hand side. That balances out with the -1 charge that's on the right-hand side. So this is the half reaction that represents the transformation of chlorate to chloride. Notice that electrons are gained here. They're on the reactant side. Therefore, even though we might not have known right at the start, we can identify that this reaction is a reduction half reaction. It shows the gain of electrons. We'll come back to this half reaction shortly, but first I want to apply the same type of logic to the second half reaction, which we now know must be the oxidation half reaction. We should expect that eventually in treatment of this process, sulfur dioxide becoming sulfate, we should expect the production of electrons. So let's balance atoms and charges. We have 1 sulfur on both sides. Sulfur is balanced. But on the left-hand side, we have 2 oxygens, whereas on the right, we have 4. There's no way for us to use coefficients in front of the existing substances to balance oxygens without throwing sulfur out of balance. The best we can do is add a new substance on one side that contains oxygen. And an acidic solution, a substance that contains oxygen, is water. I'm going to add 2 water molecules to the left-hand side of this reaction, giving me 2 plus 2, 4 total oxygen atoms. When I do so, though, I also introduce 4 hydrogens. So I'm going to need to balance that on the right-hand side. I'll use H plus to balance hydrogen. Now I've got an appropriate number of each type of atom on both sides of a chemical reaction. 4 hydrogens, 4 oxygens, and 1 sulfur on each side. On the left-hand side of this reaction, there is 0 charge because we're dealing with 2 neutral compounds. Whereas on the right-hand side of this reaction, there are 2 negative charges from sulfate and a positive charge from every one of the 4 hydrogens. 4 positives and 2 negatives give us 2 positives. To compensate for those 2 positives, and to make the net charge on the right-hand side 0, we're going to add 2 electrons to this right-hand side. And sure enough, like we would expect, this half reaction results in the production of electrons. We no longer have a 2 plus charge on the right-hand side. Taking into account these added electrons, we now have a 0 charge on this right-hand side. Because electrons are produced in this half reaction, it must be the oxidation half reaction. Now that we have both of our half reactions written, I'm going to make sure that each reaction has the same total number of electrons and add the 2 reactions together to get an overall balanced reaction. So step 3 of this process, multiply one or both of the reactions by a whole number in order to achieve the same total number of electrons produced as consumed on opposite sides of this reaction arrow. In the top reaction, we have 6 electrons consumed, but in the bottom reaction, we have 2 electrons produced. We're going to need to multiply our oxidation half reaction by 3 in order to compensate for the 6 electrons consumed in the reduction half reaction above. So let me bring that half reaction down. When we multiply this bottom reaction through by 3, what we end up with are 6 waters, 3 sulfur dioxides, 3 sulfates, 12 H pluses, and 6 electrons. We're going to add these 2 half reactions together. We'll cancel out anything that appears the same on both sides of a reaction arrow, so that when we add these 2 reactions together, all of the electrons will go away because there are 6 on the left-hand side, 6 on the right-hand side. What's more, there are 3 water molecules on the right-hand side in the bottom reaction. We can take away 3 from either side. But that doesn't completely deplete all the water molecules on the left-hand side. We'll still have 3 left. We have 6 H pluses on the left-hand side. We can take away 6 from each side. But again, that doesn't deplete all of the hydrogen ions. On the right-hand side, we still have 6 left. Everything else is a unique substance. So we can say that in the overall balanced redox reaction for this process, we have 3 H2O reacting with 3 SO2 and ClO3 minus to produce 3 sulfates, 6 H plus cations, and chloride. This is the balanced redox reaction that shows us how this skeleton reaction, a reaction containing just an oxidizing agent and reducing agent, is balanced in acidic solution. This is our ultimate balanced equation. Let's do some more examples of balancing reactions. As practice, if you followed along carefully on the previous slide, you should try to balance this reaction between dichromate and iodide occurring in acidic solution. So pause the video here and spend a few moments trying to balance this reaction. So once more, recall that in acidic solution, there are three major species that we can take advantage of for the purposes of balancing a redox reaction: water molecules, hydrogen cations, and electrons. We can split our redox reaction into two half reactions. It doesn't matter which half reaction we focus on to begin, because we'll figure out whether it's oxidation or reduction eventually. Somehow dichromate produces chromium. To deal with this reaction, we're going to need to balance atoms and then balance charge. To balance atoms, we'll see that we need 2 chromiums on the right-hand side, so I'll put a coefficient of 2 in front of the Cr3+. But we also need 7 oxygens. We don't have anything that contains oxygen right now, so I'm going to add 7 waters to the right-hand side, which in so doing produces 14 hydrogens on the right-hand side. To deal with that, I'm going to introduce 14 hydrogens in the form of H+ on the left-hand side. As it stands right now, the left-hand side has 14 positive charges from hydrogens and 2 negative charges from dichromate, for a total of 12 positive charges. And the right-hand side has 3 positive charges from each chromium, and there are 2 chromiums. So there are a total of 6 positive charges on the right-hand side. The numbers of atoms are balanced, but the charges are not. To balance charge, I'm going to add electrons to a side that's more positive. 12 plus is more positive than 6 plus, so I'll add enough electrons to the left-hand side to balance charge. I need 6 total electrons on the left-hand side. And now our charges are balanced. We can recognize this as our reduction half reaction because in this half reaction, electrons have been gained. They are part of the reactant's side. Therefore, as we deal with iodide becoming iodine, we should expect that that process represents our oxidation half reaction. In this second half reaction, somehow iodide transforms into iodine, I2. We need to balance numbers of atoms first. We can do so by putting a coefficient of 2 on the left-hand side. That's easy. There are no other atoms aside from iodide to balance. So we're good at atoms. But now we need to balance charge. How many total charges on the left-hand side? 1 from each iodide and 2 iodides in total. So 2 negative charges on the left-hand side. How many total charges on the right-hand side? 0. We're going to add electrons to the side that has a more positive value. 0 is more positive than -2, so we'll add electrons to this right-hand side. We need 2 electrons to balance charge. And sure enough, like we'd expected, in this half reaction, electrons are produced. This represents the oxidation half reaction for this redox. To balance the overall reaction, we'll add these 2 redox reactions together. But first we need to make sure that we have the same total number of electrons consumed and produced. To accomplish this, what I'm going to do is multiply the oxidation half reaction by 3. That will give me 6 electrons produced in the oxidation half reaction. Let me rewrite that now. It should look just like this. Now we can add the reduction and oxidation half reactions together to get an overall reaction. We can get rid of anything that's the same on opposite sides of our reaction arrow. 6 electrons go away. Everything else is unique to each half reaction. We have 14 H pluses, a dichromate, and 6 iodides on the left-hand side. We're left with 2 chromium 3s, 3 iodines, and 7 waters on the right-hand side. This must be our balanced redox reaction for the skeleton reaction shown up above. We can take a similar approach to balancing redox reactions that occur in basic solutions. However, in a basic solution, our major species are water, electrons, and hydroxide ions, not H+ cation ions. So really, it's the hydroxide ions that form the significant difference in how we treat basic solution redox chemistry versus acidic solution redox. We'll do everything the same exact way that we approached balancing reactions that occur in acidic solutions, right down to using H+ cation ions, except we'll take one additional step at the very end of our process. At the end, we're going to add 1 hydroxide ion to both sides of our overall reaction for every H+ we have present. The reaction will therefore generate H2O on the side that had H+ to begin with, and will generate an excess of hydroxide ions on the opposite side, like we would expect by virtue of our redox reaction occurring in a basic solution. Let's do an example so you can see how that works. To begin, let's balance the redox reaction that occurs in basic solution between permanganate and oxalate to form MnO2 and CO3 2-. We'll start by writing out half reactions. It doesn't really matter which is which quite yet, so long as we know that MnO4- somehow transforms into MnO2. We need to balance atoms, then balance charge. We have 1 manganese on both sides of this reaction, 4 oxygens on the left-hand side, and 2 on the right-hand side. We need to balance oxygen, but putting a coefficient in front of either side's substances would throw off our manganese balance. So as an alternative, let's use water to balance oxygen. I'll put 2 H2Os on the right-hand side. This also produces 4 H's on the right-hand side, so I'll add 4 H pluses to the left-hand side. And in this way, we balance atoms. On the left-hand side, we have 4 positive charges and a negative charge. That's 3 positive charges overall. We don't have any charge whatsoever on the right-hand side. So that suggests that we need some electrons on our left-hand side, specifically 3 electrons to balance charge. Now we have 3 negatives, 4 positives, and 1 more negative. 0 total charge on our left-hand side. This process represents the gaining of electrons, therefore this must be the reduction half reaction that we've just written out. We should expect that the next half reaction we write will represent the oxidation half reaction and the production of electrons. In that half reaction, somehow C2O4, 2-, converts into carbonate, CO3, 2-. Balance atoms, then balance charge. we have 2 carbons on the left-hand side. We're going to need 2 carbons on the right-hand side. We have 4 oxygens on the left-hand side. Right now we have 6 oxygens on the right-hand side. We're going to need to compensate for those oxygens. I'll do so by adding 2 waters to the left-hand side, which also introduces 4 hydrogens to that left-hand side. I'm going to have to add 4 hydrogens to the right-hand side in the form of H+. And in that way, we balance atoms. Now for charge. On the left-hand side, no charge at all from water, a 2 negative charge from oxalate. Overall, a 2 negative charge on this left-hand side. On the right-hand side, 2 carbonates, each with a 2 minus charge. That's 4 negatives. From our H+, we have 4 positive charges. That's 4 positives. So we have 0 total charge on this side, 2 negative total charges on the left-hand side. So I need to bring the total charge on the right down by 2. I'm going to add 2 electrons to this right-hand side, and in so doing, we verify that this is indeed our oxidation half reaction. Next, make it so that the electrons consumed in the reduction half reaction are equivalent to the electrons produced in the oxidation half reaction. To do this, I'm going to find the smallest whole number by which I can multiply each half reaction to make the number of electrons equivalent. I'm going to say that the equivalence in electrons occurs when we have 6 produced and 6 consumed. I'll multiply the reduction half reaction by 2 and the oxidation half reaction by 3. And here's what we'll end up with. In the modified reduction half reaction, we have 6 electrons reacting with 8 protons, 2 permanganetes, to make 2 manganese dioxide, 4 water. Reduction half reaction. In the oxidation half reaction, 6 water molecules react with 3 oxalates to form 6 carbonates, 12 H+ cations, 6 electrons. When we add these 2 reactions together and get rid of things that are the same on opposite sides of our reaction arrow, we'll end up canceling out electrons entirely. 6 electrons produced in the oxidation half reaction cancel with 6 electrons consumed in the reduction half reaction. We'll notice that we have 8 protons on the left-hand side in the reduction half reaction, 12 on the right-hand side in the oxidation half reaction. I can take away 8 from that. We have 4 water molecules produced in our reduction half reaction, 6 consumed in our oxidation half reaction. I can take away 4 waters from both sides. Everything else is unique. We're left with 2 MnO4 minuses, 3 C2O4 2 minuses, and 2 waters on the left-hand side. On the right-hand side, 2 MnO2, 6 carbonate, and 4 H+. If this reaction had occurred in an acidic solution, this would have been the end of it. But it doesn't. This reaction occurs in basic solution, where there's not an excess of H+ cations, there's an excess of hydroxide anions. There's one more thing that we have to do here in order to account for that excess of hydroxide ions. Our final step will be adding as many hydroxide ions to both sides of our chemical reaction as we have hydrogen cations. We have 4 hydrogen cations I'm going to add 4 hydroxide ions to both sides of this reaction. When I do so, this whole group of stuff, 4 H pluses and 4 OH minuses, become 4 H2Os, and we place the H2O in the place of H plus plus OH minus. Now we have 2 H2Os on the left-hand side, 4 on the right-hand side. I can simplify this equation down by subtracting the 2 H2Os from both sides. When we do this, we're left with just 2 H2Os on the right-hand side. We still have the 4 added hydroxide ions on the left-hand side, so we'll move that up and place it right in the reaction in its space on the reactant side. There's nothing more for hydroxide ion to simplify with, so this becomes our final balanced redox reaction. 2MnO4 minus plus 3 C2O42 minus plus 4 OH minus react to give us 2MnO2 plus 6 CO32 minus plus 2 H2O. As a next step to practice, I challenge you to balance this reaction between MnO4 minus and iodide in basic solution to produce MnO4 2 minus and iodate IO3 minus. Come back when you're done for a solution. To solve this problem, I've written out 2 half reactions in the reduction half reaction. We need 1 electron gained by MnO4 minus to become MnO4 2 minus. In the oxidation half reaction, 3 water molecules react with iodide to form iodate, 6 H pluses, and 6 electrons. We multiply the reduction half reaction by 6 to make the number of electrons the same in both half reactions. That gives us a coefficient in front of everything of 6. We add these 2 half reactions together, get rid of anything that's the same on both sides of our reaction arrow. 6 electrons go away. Everything else is unique, so we'll be left with 3 water molecules reacting with 6 MnO4 minus and iodide to make 6 MnO4 2 minus iodate and 6 H plus. We know though that this reaction occurs in basic solution. So anywhere we see H plus, we're going to have to add an equivalent number of hydroxide ions, and we'll do so to both sides of our reaction arrow. This right-hand side turns into 6 water molecules instead of 6 H pluses and 6 OH minuses. We can subtract 3 water molecules from both sides. So that will be left with 3 water molecules at the end of this. We still have 6 OH minuses to add to the left-hand side. Ultimately, what this looks like is as follows. Six MnO4 minus reacts with I minus and 6 OH minus to produce 6 MnO4 2 minus, IO3 minus, and 3 H2Os. In what remains of this chapter, we're going to talk about applications of redox reactions in order to generate electrons that can do useful work for us. What we've seen so far is that an oxidation half reaction produces electrons. Those electrons are shuttled to a substance that consumes those electrons for a reduction half reaction. The theory behind electrochemistry is that while those electrons are in transit, we can harvest them to do some work for us, like say, operate a light bulb. In an electrochemistry reaction, we take advantage of redox to do useful work. And we can set up any number of electrochemical cells. The simplest type of electrochemical cell is one that operates on the basis of a spontaneous chemical reaction. A voltaic or galvanic cell uses a spontaneous redox reaction to generate electrons through an oxidation half reaction and shuttle those electrons to a reduction half reaction. The experimental design for this reaction consists of two reaction cells or locations, one in which the oxidation half reaction occurs to generate electrons in the first place, and the other where those electrons travel to facilitate the reduction half reaction. We give special names to the cells that contain either the oxidation or the reduction half reactions. The cell where the oxidation half reaction occurs is the anode, and the cell where the reduction half reaction occurs is the cathode. So at the anode of an electrochemical cell, electrons are produced. At the cathode of an electrochemical cell, electrons are consumed. Therefore, we expect electrons to move from anode to cathode. We can intercept them along their route and have them do useful work for us. And we're also going to have to remember which electrode corresponds to which half reaction. The anode corresponds to the oxidation half reaction. We can remember anox to help us remember anodes and oxidation. And we can remember that a cathode is where reduction happens if we remember a red cat. Reduction happens at the cathode. At the anode, oxidation occurs. Two animals to help us remember oxidation and reduction: anox and a red cat. Practically speaking, we need a few key components to create a voltaic electrochemical cell. And luckily, I have some drawing tools at my disposal, so I'll help you visualize drawing these things. We're going to have, firstly, two beakers. One that contains an anode and the other that contains a cathode. So here are two beakers. I'm going to draw my anode on the left-hand side. So we'll say that this beaker will represent our anode. This is where oxidation occurs. And this beaker will represent my cathode. This is where reduction occurs. So electrons will be produced here at the anode, consumed here at the cathode. These two beakers contain solutions. These solutions are electrolytes. And what's more, they also contain electrodes. These electrodes maybe are metallic substances, perhaps rods of, say, zinc and silver. So here's a zinc rod or a zinc electrode, and we'll make another one that can represent our silver rod or silver electrode, and we'll place it in the cathode solution. So here is zinc and here is silver. We're going to need to connect these two electrodes with a wire so that electrons can transfer. Otherwise, no redox reaction can occur. because a redox reaction is predicated upon electron transfer in the first place. So we'll use a wire to connect these two together. But maybe in the middle, we'll place a light bulb so that while these electrons are traveling, maybe they can stay a little while and illuminate a light bulb. So here we are. We have an electrochemical cell that can illuminate a light bulb. What do we need in these solutions in order to make that happen? Well, in our anode, we need to have some vehicle for our zinc to give up electrons. At our anode, because oxidation occurs, zinc is going to somehow go from metallic Zn into zinc cation, producing electrons. So zinc is going to come into solution as Zn2+. Eventually, over time, therefore, we're going to eat away at our zinc and more of our zinc will decompose. Meanwhile, on the other side of our reaction, at the cathode, reduction is occurring. Electrons that are traveling to our cathode meet up with our silver electrode. Those electrons could react with silver cations, if there are any in solution, and generate even more metallic silver at that electrode. So what's going to happen is that silver cations, if they're in solution, will start to accumulate on this electrode. Therefore, over time, we expect that this electrode will gain some mass as it accumulates more and more silver. So at both electrodes, we need some electrolyte solution that at least contains cations, and in order to contain cations must contain anions too. Perhaps the anion in each is something like nitrate. Electrons therefore will flow from this anode, where they're produced through an oxidation half reaction, through this system to the cathode, where they're consumed via this reduction half reaction. As these electrons flow, we can imagine one more complicating factor. At the anode, over on this side, as oxidation occurs, more and more zinc cation is being produced in solution. Over time, excess positive charges are going to accumulate in this half cell. Similarly, at the cathode, over time, more and more cations are being consumed over time, leaving us with a dearth of positive charges, or similarly, a buildup of negative charge on this side. Eventually, these disparities in charge, too much positive charge on the left-hand side in the left-hand cell, and too much negative charge on the right-hand side in the right-hand cell, will cause this reaction to stop and no longer be spontaneous. If we want this reaction to continue indefinitely, we've got to have some way to balance charge, in addition to just balancing redox reactions. To accomplish this, we need some sort of salt bridge, maybe just a strip of chromatography paper that is draped over these two cells that allows for the transport of ions rather than electrons. This salt bridge will allow a buildup of positive ions on the left-hand side to be equilibrated with a buildup of negative ions from the right-hand side of these electrochemical cells. This salt bridge is maybe dipped in something like sodium nitrate that contains inert ions that won't participate in the redox reaction we're interested in. But sodium ions can travel to a place where positively charged ions are being consumed while nitrate ions can travel to the place where positively charged ions are being built up. Overall, in this reaction, now we can say that indefinitely until one of our electrode's components runs out, our reaction will proceed so that zinc produces electrons at the anode. Those electrons travel through a device and we make them do useful work for us. And eventually, as those electrons finish up their task, react at the cathode to help a reduction half reaction. Our oxidation half reaction in this overall redox reaction looks like this. Zinc becomes zinc cation and produces 2 electrons. This reaction occurs at the anode because oxidation occurs at the anode, anox. The reduction half reaction looks like this. Electrons react with silver cations to produce metallic silver. This reaction occurs at the cathode because all reduction occurs at the cathode, red cat. If we add these 2 half reactions together to get an overall balanced reaction, notice that we'll have to multiply the reduction half reaction by 2 in order to get an equivalent number of electrons on both sides of our reaction arrow. Therefore, we end up with zinc reacting with silver with a coefficient 2 to produce zinc 2 plus and silver metal with a coefficient 2. This is our overall reaction. One more way to write the exact same information is to reproduce all of this in shorthand. In shorthand notation, we write all of the components of our anode on the left-hand side of a single line. The components of our anode include solid zinc and zinc in an aqueous phase as a cation with a 2 plus charge. This solid vertical line represents a difference in phase or a phase boundary between solid and aqueous. We had a solid electrode for zinc and a solution that contains zinc cation. This electrode, this anode, is separated from another electrode, the cathode, which contains silver cations in aqueous solution and in a separate phase, silver metal. This double vertical line represents a physical separation, not just a phase boundary, but a separation in space. All of the contents of our anode, zinc and zinc cations, are over in this beaker on the left. All of the contents of our cathode, silver and silver cations, are in this beaker over here on the right. They are physically separated in space. This shorthand notation helps us quickly identify what materials exist at the anode, where oxidation occurs, and which materials exist at the cathode, where reduction occurs. We list the solid contents of the anode separated by a single vertical line from other phases at that anode. And we distinguish one electrode from another using double vertical lines. This shorthand shows exactly the same reaction that we saw on the previous slide, written out in full form. The left will always be contents at the anode. The right will always be contents at the cathode. So these occur in alphabetical order: anode, cathode. Separated by a double vertical line. So back to the previous slide then. One final thought on this is that it would be nice if we could determine how much useful work our electrons are doing as they power some device moving from anode to cathode. If only we could measure something about an electrical potential, say, or a voltage, as these electrons are produced at our anode and consumed at our cathode, perhaps we could accomplish saying something about the useful amount of work they're doing for us. To accomplish this, we could write down the standard reduction potential, or E, for each half reaction. E naught is a standard reduction potential. It tells us effectively how much voltage is generated relative to some reference electrochemical cell by a given half reaction. By default, half reactions are represented as reduction in comparison to this nebulous reference potential. Therefore, they are reduction potentials by default. There are E values tabulated for all sorts of half reactions. There's an E value for this reaction of zinc, and there's an E value for silver, always by default given in the form of reduction. Silver reducing to silver metal is a favorable process. It tends to be spontaneous. But zinc cations reducing to zinc metal is not a very spontaneous process. Zinc would much rather be in the zinc 2+ oxidation state. If we look up tabulated values of these E quantities for each one of these half reactions, what we'd find is that for zinc, this standard reduction potential is negative 0.76 volts. Whereas for silver, it's positive 0.80 volts. Eventually, what we're going to do is come up with a value for the overall cell potential, which we'll call E cell. The overall voltage of our cell potential comes from taking into account how well the cathode reduces versus how well the anode oxidizes. E cell will always be written as the standard reduction potential associated with our cathode minus the standard reduction potential associated with our anode. This is an equation that you should become used to. Here, E cell for this reaction of silver and zinc is 0.8 minus negative 0.76. For a total value of 1.56 volts. We say that the cell potential, the voltage that's generated by this electrochemical cell, is 1.56 volts. Every half reaction has one of these standard reduction potentials, typically given for a reference temperature and in reference to a particular reference electrode, which we'll learn about more in future courses. For right now, what you should be concerned with is that you can find a reference list of all of these standard reduction potentials in Appendix D of your textbook or another trustworthy source. By default, these half reactions are always given in the form of reduction, where electrons are gained, and they're ranked in order from things that really like to be reduced to things that really hate to be reduced. Things that really like being reduced are at the top of this list, and things that really hate being reduced are at the bottom of this list. They're ranked from the highest positive value of E naught to the most negative value of E naught. And this result gives us one way to compare qualitatively E values. The greater and more positive an E value for these standard reduction potentials, the more spontaneous reduction is. And conversely, the more negative these E values, the less spontaneous reduction is. And we know that if a reaction is non-spontaneous now in one direction, then it must be spontaneous in the opposite direction. So if reduction is not spontaneous for negative values of E naught, then the opposite of reduction is spontaneous. So the more negative E, the more spontaneous oxidation becomes. Half reactions represented near the top of this list represent happily reduced substances with very high positive values of E. Substances represented at the bottom of this list represent substances that are opposed to reduction with negative values of E. Things at the bottom of this list would much rather oxidize, reverse these reactions, and produce electrons rather than acquire them. Reversing a reaction changes the spontaneity with which a process occurs and therefore switches the sign on this E value. Thus, because oxidation occurs at an anode and all of these cell potentials are given by default as reduction potentials, the overall cell potential for something that contains both an anode where oxidation happens and a cathode where reduction happens is given as the potential associated with our cathode. This is where reduction occurs. Red cat. Minus the standard potential for our anode. A negative sign or a minus because at the anode oxidation occurs, anox. Overall, we calculate the effect of having both a cathode and an anode in terms of this so-called standard cell potential. So, this is a quantity that we are going to be particularly interested in for the remainder of this chapter. This is our standard cell potential for an electrochemical cell. We'll refer to this standard cell potential as we tie this concept of redox chemistry back to both equilibrium and thermodynamics. In order to obtain this standard cell potential, the overall potential for a redox reaction, E cell, we need to use reference lists like Appendix D, the table that I showed in your previous slide, or a table that's available on things like your homework site, to determine the standard reduction potential for the materials at our cathode and subtract from that the standard reduction potential for materials at our anode. It's important to point out and clarify that these standard reduction potentials do not depend upon the stoichiometric amounts of material present at our cathode or our anode. We don't have to worry about coefficients, say, from overall balanced equations when we reference that appendix. All we have to worry about are how many electrons that were transferred in a given half reaction. What we say is that in calculating this standard cell potential, if the result is greater than 0, then that electrochemical cell represents a redox reaction that's spontaneous. And as a spontaneous redox reaction is capable of powering a voltaic cell, one that can generate electrons that do useful work for us. If the standard cell potential E cell is less than 0, if it's negative, then our redox reaction is non-spontaneous. And if we want it to proceed, we have to continuously input electrical energy in order to power that electrochemical cell. In order to tie this concept back to thermodynamics, we need a bridging unit or constant to help us relate things like Gibbs energy to voltage like we'd get from a standard cell potential. Gibbs energy from back in chapter 20 we recall as being delta G, a measure of the spontaneity of a chemical process. This Gibbs energy is related to the standard cell potential for an electrochemical reaction through the Faraday constant, F, named after Michael Faraday, who did pioneering work in electrochemistry. The Faraday constant, F, has a value of 96,485 joules per volt per mole of electrons. For those of you who have taken physics or are interested in it, Faraday's original observation is that a mole of electrons, or a standard quantity of electrons, has multiples of the same total charge. The Faraday constant has a value of 96,485 coulombs, a measure of electrical charge, per every 1 mole worth of electrons, or standard set quantity of electrons. From physics, 1 joule per 1 volt is the definition of 1 coulomb. A coulomb is how much energy is associated with a particular voltage, or in other words, voltage is how much energy is associated with a given charge. Therefore, we can rewrite Faraday's constant in its form given above. Faraday's constant, F, 96,485 joules per volt per mole of electrons. This quantity of joules is much more directly obvious to us at this point, a measure of energy for a chemical reaction than a quantity like coulombs might be. Thus, to get units of energy all by themselves, we would need to multiply this Faraday constant by something that's got quantities of volts and another quantity in moles. What that ultimately looks like for us is that the energy associated with an electrochemical cell, delta G, under standard conditions is given as N, number of moles, times the Faraday constant, F, times the standard cell potential in volts for a redox reaction. We're going to place a negative sign out in front of this as well, because we said that anytime E cell is greater than 0, we're representing a spontaneous chemical process. In chapter 20, we said that delta G being less than 0 represents a spontaneous chemical process. So now we have two different competing measures of spontaneity. A spontaneous process has a delta G that's negative, less than 0. And it has an E cell that's positive in electrochemistry, greater than 0. So a spontaneous electrochemical reaction could be represented by standard Gibbs energy less than 0, by standard cell potential greater than 0. And conversely, a non-spontaneous electrochemical reaction has a delta G that's positive, greater than 0, or an E cell that's negative, less than 0. So let's keep that as an aside. The equation that links standard cell potential to thermodynamics is this one. Here we have Gibbs energy, delta G, under standard conditions, is equal to negative N. This is the number of moles of electrons transferred. This is the simplest way to get an equivalent number of electrons produced in an oxidation half reaction as consumed in a reduction half reaction. It's the equivalence in electrons in two half reactions. It's not electrons added together, it's just how many electrons we have produced or consumed in a balanced redox reaction. F is our Faraday constant, and E cell is our standard cell potential. This is the thing we defined on the previous slide. Its value is given as the standard reduction potential for our cathode minus the standard reduction potential for our anode. And what's more, because we know that thermodynamics is intricately tied to equilibrium, we can also relate the standard cell potential to our equilibrium constant for a chemical reaction. Because delta G is equal to negative RT times the ln of K, as we all now have memorized from chapter 20, delta G is equal to negative RT ln of K for a reaction where K is our equilibrium constant for that reaction, and delta G is equal to negative NF E cell, as we see here for an electrochemical reaction. Negative RT times the ln of K must be equal to negative NF E cell. If we solve this equation for just E cell by dividing through by negative N and F, we end up with this result. The cell potential, the standard cell potential for an electrochemical reaction is equal to RT over NF times the ln of K, our equilibrium constant. Here we have a way to relate the standard cell potential for a redox reaction to the equilibrium constant for that reaction. R is our ideal gas constant, given in energy units, 8.3145 joules per mole per Kelvin. T therefore must be our Kelvin temperature. N is the number of electrons transferred in a redox reaction, the equivalence point in electrons produced and consumed in an oxidation or reduction half reaction. F is Faraday's constant, and K is our equilibrium constant for our redox reaction. So let's use all of the equations that we've learned about so far in this example problem. In this example, cadmium reacts with copper 2 cations to produce copper and cadmium 2. The Gibbs energy change for this reaction under standard conditions is negative 143 kilojoules per mole. This suggests to us that this reaction is indeed spontaneous because delta G is negative. We should expect that this reaction could be used to power an electrochemical voltaic cell. The first thing that we're going to do is find the equilibrium constant for this reaction at 25 degrees Celsius. We should expect that the equilibrium constant for this reaction is much greater than 1, because when delta G is negative, this value K is large. Then we're going to verify from that equilibrium constant that the standard cell potential for this reaction is 0.74 volts. We can show that the standard cell potential for this reaction is 0.74 volts by using this equation for E cell, the standard reduction potential for our cathode minus the standard reduction potential for our anode. To identify our cathode and our anode, we need to figure out which substance oxidizes, which substance reduces. Cadmium goes from 0 oxidation state to a 2+ oxidation state, represented by this first half reaction shown here. As cadmium goes from 0 to 2+, we say that it oxidizes. Oxidation is associated with the anode of an electrochemical cell, An-ox. Meanwhile, copper goes from a 2+ oxidation state to a 0 oxidation state. It goes down in oxidation state, so we say it has reduced. Reduction is associated with the cathode, red cat, for an electrochemical cell. Copper's standard reduction potential is given by this second half reaction. Overall, the standard cell potential for this reaction is the standard reduction potential associated with our cathode, represented by copper. That's positive 0.34 volts, minus the standard reduction potential for our anode. Our anode is represented by cadmium, whose half reaction shown here tells us that the standard reduction potential for it is negative 0.40 volts. 0.34 minus negative 0.40 is indeed 0.74 volts. We're going to verify this a second time through calculations using thermodynamic and equilibrium data we show below. So let's find the equilibrium constant for this reaction at 25 degrees Celsius. To accomplish that, we'll use the most recent equation that we've come up with, the standard cell potential as a function of equilibrium constant. E cell is equal to RT over NF times the ln of K. In this equation, R, T, and F are either constants or given. We're going to have to figure out N, the number of moles of electrons transferred. To do that, let's write out the half reactions represented by this overall redox reaction. In one half reaction, cadmium somehow gets converted to cadmium 2+. We can balance both atoms and charge in order to assess this half reaction. We have 1 cadmium on both sides of this reaction arrow, so atoms are balanced, but we have 0 charge on the left-hand side, 2 positive charges on the right-hand side. We're going to need to add 2 electrons to this right-hand side to identify charge balance. Separately, copper somehow goes from 2+ to 0 oxidation state. Again, balance atoms and charges, and we'll see that we have enough coppers on both sides of our reaction arrow. All we need to do is balance charge. 2 electrons are used to reduce copper 2 to copper in this reaction. From this, if we added these 2 reactions back together just as they stand right now, we would achieve the same reaction that we showed up above. 2 electrons are consumed, 2 electrons are produced. The overall reaction is cadmium plus copper 2 makes cadmium 2 plus copper. The reason that we did this, though, was to identify how many electrons were transferred. 2 electrons are produced, 2 electrons are consumed. The number of electrons either produced or consumed, the number of electrons transferred, is N in this equation. N is 2 electrons. 2 electrons were produced so that the same 2 electrons could be consumed. There's not a difference in these 2 electrons. Therefore, our standard cell potential can be calculated as follows. It's R, the ideal gas constant, in joules per mole per Kelvin, times T in Kelvin, which is 298, divided by N, number of moles of electrons transferred, times F, Faraday's constant, in joules per moles of electron per volt, multiplied by the natural log of the equilibrium constant, K. Here, we know the value of E cell is equal to 0.74 volts. So we can plug that in where we see E cell in this equation. We can rearrange this equation to solve for K if we multiply both sides by the entirety of the denominator, 2 and 96,485. Then divide both sides by 8.3145 and 298. When we do that, we should end up with something like 57.63 is equal to the natural log of equilibrium constant K. Now we have to get rid of a natural log, so we can raise e to the power of both sides. E to the natural log of a number just gives us back that number. E to the 57.63 is a huge number. It's something on the order of 1.1 times 10 to the positive 25th power. That's gigantic, and that's what we would expect for an equilibrium constant for a very spontaneous reaction, one with a very largely negative value of delta G. We could have alternatively found K through our other equation, one that relates delta G to K from our thermodynamics chapter in chapter 20. So let's do that and verify that we get, for all intents and purposes, the same result. Alternatively, we remember from our discussion of thermodynamics that delta G is equal to negative RT times the ln of K. Delta G is given in this reaction as negative 143 kilojoules per mole, or negative 143,000 joules per mole. R, our ideal gas constant in joules per mole, is 8.3145. Temperature in Kelvin is still 298 K. And the ln of K can be solved by dividing both sides by negative 8.3145 and 298. We end up with the ln of K is equal to 57.7. And again, to solve for K, we raise e to the power of both sides. Again, we get a huge number, about 1.1 times 10 to the positive 25th power. So regardless of which method we use, we can get our equilibrium constant, K, back. We can verify that this reaction has a standard cell potential of 0.74 volts by looking up each individual cell potential for each individual half reaction. Overall, there are 3 pieces of evidence that point us towards this reaction being spontaneous. For one thing, our reaction is spontaneous because delta G is negative. Because our overall standard cell potential is positive. Because our equilibrium constant is much, much greater than 1. All of these things we've learned as a culmination of this semester are indicative of spontaneity. Gibbs energy less than 0, standard cell potential greater than 0, equilibrium constant greater than 1. All suggest that this reaction will proceed towards products. And like we discussed in our chapter on thermodynamics, standard conditions are a good benchmark, but are not exhaustively inclusive of all of the possible conditions we could find a chemical reaction occur at. A non-standard condition in the electrochemistry sense implies that concentrations aren't 1 molar, or that reactants or anodes or cathodes aren't in their standard state or at equilibrium, in order to determine the cell potential, just E cell, from a standard cell potential under ideal conditions or standard conditions, we use the Nernst equation. So what we're going to do here is derive that Nernst equation. Standard cell potentials are E cell. So these occur under standard conditions. But anytime that we're not at standard conditions, like when we have a reaction that's not at equilibrium, say, we have to calculate E cell, not E naught. E cell under non-standard conditions, often not at equilibrium for our case. Are used in a similar way or a similar vein to the way in which Gibbs energies under non-standard conditions were used. Remember from our thermodynamics chapter that delta G without the naught symbol was given as delta G with a naught symbol under standard conditions plus RT times the ln of Q, where Q is a reaction quotient, a snapshot of our reaction at a given point in time, regardless of whether it's at equilibrium or not. We know that delta G under standard conditions is equal to negative NF E cell under standard conditions. So it should stand to reason that delta G under non-standard conditions is equal to negative NF E cell under non-standard conditions, just removing the naught sign. Therefore, negative NF E cell under non-standard conditions is equal to negative NF E cell under standard conditions, plus the RT ln of Q. To simplify this equation, we could divide everything through by negative NF. Those terms go away in the first two quantities, and we're left with E cell under non-standard conditions is equal to E cell under standard conditions with a naught symbol minus RT over NF times the ln of Q. This equation is extremely important for tying together standard conditions to non-standard conditions as a function of equilibrium or lack thereof in our reaction quotient Q. This is the Nernst equation. In the Nernst equation, Q is our reaction quotient. Remember that our reaction quotient is written exactly the same as our equilibrium constant, except that our reaction quotient is universally applicable. It can apply at any set of conditions and doesn't have to be restricted to just equilibrium. R is our ideal gas constant, T our Kelvin temperature, and the number of moles of electrons transferred in a redox reaction, F the Faraday constant. So suppose we wanted to determine the concentration of iron 2 cations that are needed to produce a non-standard cell potential of 1.03 volts when this reaction is carried out using a concentration of copper 2 of 0.3 molar. In order to accomplish this calculation, we're going to need to know something about the ratios of concentrations of substances, for which we'll need to call back our understanding of equilibrium. We're going to need to know something about the overall reaction's net transfer of electrons. We're going to need to understand how to calculate the standard cell potential, and we're going to have to reference some standard reduction potential tables. If we were in class together, I would have standard reduction potential tables for you. But because we're not, I'll just give them to you as we work through this equation. So let's identify what we know already. From our Nernst equation, the only quantity with which we are provided is 1.03 volts. This is our non-standard cell potential, E without a naught symbol. We'll assume, for the sake of simplicity, that this reaction is carried out at 298 K, but everything else remains for us to be determined. So, where to start? We need a standard cell potential, we need a number of moles of electrons transferred, we need a reaction quotient. The best way to get that is to come up with a reaction, or in this case, half reactions that show us how this redox is carried out. Somehow, one of our half reactions shows us that iron becomes iron 2+. Balancing this half reaction requires that we balance atoms first, which aren't already balanced, and then charges. We'll add 2 electrons to the right-hand side. This is therefore indicative of our oxidation half reaction because electrons are produced. Where does oxidation occur? Anox. Oxidation occurs at the anode. Like I said, I would have you look up on your own the standard reduction potential for this reaction if you were in class with me. But here I'll give it to you. It's 0.44 volts and it's negative. The second half reaction of concern must be a reduction half reaction. Somehow copper 2 becomes copper solid. Atoms are balanced, we just need to balance charge. We add 2 electrons to the left-hand side of this reaction. This is indeed our reduction half reaction because electrons are gained. The standard reduction potential for copper, if we looked it up, would be positive 0.34 volts. This treatment of half reactions does several things for us. It tells us, for one thing, how many electrons were transferred in the course of this reaction. It gives us the value for N. 2 electrons are produced, 2 electrons are consumed. So N is 2 moles of electrons. It gives us a means by which to identify our anode and our cathode. The reduction half reaction must occur at our cathode. The oxidation half reaction must occur at our anode. Why do we care about that? Because in order to get our standard cell potential, we need to know the standard reduction potential for the half reaction at our cathode and subtract from that the standard reduction potential for the half reaction at our anode. The overall E cell under standard conditions is the standard reduction potential at our cathode minus the standard reduction potential at our anode. Now that we've identified the cathode and the anode, we can plug in the appropriate numbers. 0.34 volts minus negative 0.44 volts. We knew that because iron is representative of the oxidation half reaction, that it must represent the anode, and vice versa for copper at the cathode. The standard cell potential for this reaction must be equal to positive 0.78 volts, therefore. So, 2 quantities, N, number of moles of electrons, and E cell, directly from this treatment of half reactions. If we were to add these 2 half reactions together, we should get our overall reaction. Our overall reaction has no electrons in it in net, just solid iron plus copper 2 cations react to give us iron cations plus copper. We know an E cell for this reaction already. What we're going to be after here is figuring out an expression for our reaction quotient Q. We write our reaction quotient in the same way we'd write our equilibrium constant. Concentrations of products raised to their stoichiometric coefficients divided by concentrations of reactants raised to theirs. But we don't include solids or liquids in our equilibrium constant or reaction quotient expressions. Therefore, our reaction quotient Q is given just by the concentration of iron 2+ as our product raised to the first power divided by the concentration of copper 2+ raised to the first power. And now we have a value of Q. From our problem up above, we were told that the concentration of copper in this electrochemical cell needed to be 0.30 molar. So we can plug that in our expression for Q. Q is equal to the concentration of iron divided by 0.30 molar. We were told that the non-standard cell potential that we'd like to achieve with this electrochemical cell is positive 1.03 volts. We know the value for R in joules per mole per Kelvin. We know the temperature, or at least presumed a temperature. We now have N. We know F is Faraday's constant, 96,485 joules per volt per mole of electron. We have all the information, therefore, necessary to plug into the Nernst equation and solve for the only remaining unknown, which is the concentration of iron cation we need in this electrochemical cell. So let's do that. According to the Nernst equation, E cell under non-standard conditions, in this case 1.03 volts, is equal to standard cell potential, E cell naught, given by 0.78 volts here, minus R, 8.3145 joules per mole per Kelvin, times T, 298K, divided by number of moles of electrons transferred, 2 moles of electrons, and Faraday's constant, 96,485 joules per mole of electron per volt, times the ln of Q. Here, Q is the concentration of iron 2 cations divided by 0.3 molar. And it's just as simple as this to solve this problem. As far as units are concerned, we'll get rid of things like joules, moles of electrons, Kelvin, and eventually we'll just make volts go away too. To solve, we need to subtract 0.78 from both sides. What we'll end up with on the left-hand side is therefore 0.25. That's going to be equal to this whole big mess of stuff. So let me grab that and we'll bring it down. And that whole big mess of stuff is multiplied by the natural log of Q. Concentration of iron 2+ divided by 0.3 molar. So, we're after solving for concentration of iron 2+. To accomplish that, let's multiply both sides by the denominator of this fraction out in front. 0.25 times 2 times 96,485. Then we'll divide both sides by 8.3145, 298, and keep the negative sign out in front. We end up with, once we do all that, negative 19.49 on the left-hand side. That's equal to the natural log of the concentration of iron 2 cations divided by 0.30 molar. To undo a natural log, we'll raise e to the power of both sides. E to the natural log of a quantity just gives us that quantity back. concentration of iron 2 plus divided by 0.3 on the right hand side. E to the negative 19.49 gives us 3.43 times 10 to the minus 9. One last step, multiply both sides by 0.3. When we multiply through by 0.3, we end up with a concentration of iron cations equal to 1.0 times 10 to the minus 9 molar. This result tells us that we would need a nanomolar concentration of iron 2 cations should we want to generate an electrical potential of 1.03 volts from this electrochemical cell. So, through a series of very simple, easy, fun calculations, we've been able to use virtually everything we have talked about for the bulk of this semester to solve a problem. We have taken into consideration this Nernst equation that relates a cell potential under non-standard conditions to a cell potential under standard conditions, which we can determine through analysis of individual half reactions. We can relate that also to the reaction quotient, a snapshot of our reaction that's not necessarily at equilibrium, through the equilibrium treatment of our reaction. We solved for our concentration of iron, again using the rules of logarithms that we've been talking about all semester long. As a few brief asides, I'd like to talk a little bit about some more terminology regarding redox reactions and electrochemical cells. A battery is an example of a device that operates using an electrochemical cell or cells to carry out a series of redox reactions that allows us to take advantage of useful electrons. We can classify batteries generally into two categories: primary batteries and secondary batteries. A primary battery uses a non-reversible chemical reaction. A non-reversible chemical reaction meaning one that doesn't establish equilibrium and can't be reversed or reverted back to its original form. Thus, when primary batteries' electrochemical cells have gone exhausted, they're disposable or recyclable, but not reusable. Alkaline batteries like the AA, AAA, C, or D cell batteries that you use to power lots of small electronic equipment are examples of primary batteries, as are anything that uses a button cell battery. A secondary battery is one that does work on a reversible chemical reaction, which means that we could recharge each one of these batteries in order to reconvert products to reactants and allow the whole process to go over again. The most common example that you are likely to have used is either a lead acid battery that you might find in a car or a lithium ion battery that powers more sophisticated electronic devices like phones, laptops, and so forth. In each one of these batteries, reactions can be reverted back to reactants through application of some outside source of electricity. We need to charge these batteries. But this charging process isn't 100% efficient, which means that even for these batteries, over time, we revert fewer and fewer products back to reactants. Over time, things like the lead sulfate that's produced in your car's batteries are inefficiently converted back into lead and lead oxide. And lead sulfate builds up until your car's battery can no longer operate efficiently anymore. And it's particularly noticeable under cold temperature conditions, which is why as your battery ages, it's less and less likely to be as operable when the temperature drops. A second application of these redox reactions is in preventing the corrosion of metals. Corrosion or rusting is a redox reaction that occurs when metals are exposed to oxygen and moisture in the atmosphere and thus oxidize. This is a spontaneous electrochemical redox reaction whenever E cell for this reaction is greater than 0, according to our thermodynamic treatment of electrochemistry. Think about two different metals, perhaps gold and iron. If gold were to corrode, if gold were to rust, corrosion of gold would have a reaction that looks like this. The corrosion of gold would have an oxidation half reaction represented by the oxidation of gold to something like gold 3. The reduction half reaction for this corrosion might look something like this. H plus could react with oxygen in the atmosphere and use 4 electrons to produce 2 water molecules. Overall, the standard reduction potential for each one of these half reactions can be used to calculate an E cell. Here the E cell is negative 2.76 volts. Because this value of E cell is less than 0, we say that it's not spontaneous for gold to oxidize. So gold's corrosion is not spontaneous. We don't expect that over time gold will corrode. But let's contrast this with iron. Iron can oxidize. In the corrosion of iron, we expect Fe to become something like Fe2+, and generate electrons. In a reduction half reaction, we could expect something similar, so that this is just the same on the opposite side as it was for gold. But overall, our standard cell potential is a little bit different for iron. Here, it's positive 1.52. In this case, the standard cell potential for iron's oxidation or corrosion is greater than 0, which suggests to us that iron's corrosion is spontaneous, in contrast with gold's. So we expect iron to rust, whereas we don't expect gold to rust. Gold stays gold and doesn't form oxidation layers or rust because it's not spontaneous for it to do so. Therefore, gold we consider a noble metal, a precious metal that's got high value because it always exists as gold and not as a corroded product, whereas iron corrodes spontaneously. So it doesn't exist as pure iron for very long when exposed to the atmosphere. Thus, if we want to preserve something that is made from iron, like say an iron tool or iron metal that's used for structural purposes, we'd have to do something to protect it. It is possible to prevent corrosion through chemical means. One way to do so might be to simply paint the metal that we're trying to protect. If we do so, then the paint has to corrode first before the metal underneath, because it's the surface layer of paint that's exposed to the atmosphere rather than the underlying metal. But paint can chip and paint can wear away too. So a more effective long-term solution to this problem is to coat a vulnerable metal with a sacrificial layer. This sacrificial layer will act as an even stronger reducing agent than the metal that's being protected underneath. We'll choose a metal to coat that's even better at oxidizing. Another way of saying that is that it's worse at reducing than the metal that we're trying to protect. One good choice for this purpose is zinc. Zinc is really good at oxidizing, really bad at reducing. zinc is a good choice. Because the standard reduction potential for zinc is given as negative 0.76 volts. The standard reduction potential for iron is given as only negative 0.44 volts. Zinc is worse at reducing than iron. And conversely, therefore, if it's worse at reducing, it must be better at oxidizing than iron. Therefore, zinc will spontaneously oxidize or rust before iron does. The use of zinc as a sacrificial layer has been employed for years. The process of using zinc as a protective layer or barrier against corrosion by applying zinc as a surface coat is called galvanization. Galvanized materials, or the process of galvanization, is the use or coating a material or a metal with zinc to protect it from rusting or oxidation. If you need a source of zinc, find some galvanized metal, like galvanized nails. For one final brief discussion point, I'll mention electrolytic cells, although because we are not together this semester in person, I won't belabor this point and expect you to know about it to a large extent. In a voltaic or galvanic cell, a redox reaction that's spontaneous is used to produce electrons that can do useful work for us. But if we want to generate a non-spontaneous redox reaction, we have to constantly employ an external source of electrical energy to make a reaction happen. You might wonder why we would do this. But the reason is that electrolysis, or the use of an external electrical energy source to power a non-spontaneous redox reaction, is capable of generating things like base chemicals that are used as stock for lots of different chemical reactions. For instance, the electrolysis of water can regenerate the elements hydrogen and oxygen using electrical energy to split water molecules back into its component individual elements. The electrolysis of sodium chloride is representative of one of the most widely used electrolysis industrial processes called the chlor-alkali process. It's essentially the source of chlorine for industrial purposes. We can take advantage of electrical potentials and apply a small overvoltage to generate chlorine in an electrolytic cell containing concentrated sodium chloride in solution. Again, I thought that this was worth mention, but I will not test you on it this semester in General Chemistry 2 in the spring of 2020. So, we'll have one more brief discussion on nuclear reactions, but this largely rounds out the bulk of material for the semester.